this magnet that has magnetization M. I think maybe I can bring. Okay, so you can think of this as your closely conducting wire, and this is the material with magnetization M. So what happens is that you was imagine that this is far away from the ring. So we wanna know how the flux changes for this conducting loop as you move it through this wire with a velocity v. So when it's further away, what can you say the flux? So when it's further away, the flux on that loop is going to be 0, right? So if it is far away, no magnetic, the strength of this magnet is going to be weak. So the flux is going to be 0. But as you move it closer, what's going to happen? The flux starts to increase, right? So if I have a graph, so let's say this is x, the distance, and this one is the flux phi, or rather it's time instead of x. Let's use time. So t infinity at t equals to 0, that means t equals to 0 means when this thing is further away, you started far away from the loop. So at t equals to 0, the flux is 0, but as you move it closer, as time increases, the flux increases, right? So when it enters, at some point, the strength of the magnet is going to be the same for a certain period of time until it leaves the loop. So during that time, you expect a flux that is a constant. So we are talking about ideal case, so where we have, where we assume the magnetic flux is constant, and also we assume the length of the magnet is large. So in that case, you can say the flux is constant as it passes through that. So as it passes through, the flux is constant. But once it just starts to come out, so once it reaches here and starts to move away, the flux starts to decrease, right? So you have something like that. So that is the flux as a function of time. The second part is okay. Well, I know you know this, but what we are given here is the magnetization, right? M. But if you want to know the magnetic field of a magnetized object, for this one, for example, you start from H equals to 1 over mu naught times B minus M. Yeah, minus M. So H is a result of what kind of current it is. We have shown that H exists whenever there is what kind of current? free current. So do we have any free current here? No. So no free current. So you can say H equals to 0. So in this case, 1 over mu naught B is equals to M. So you can write the magnetic field equals to mu naught M. So this is what it generates the flux. So I put there B equals to 0 for S greater than A, where A is what? A is the radius. A is of the magnetized object. That's the radius of this one. So basically, what I say is I assume a long solenoid, a long magnet, and you can basically say the magnetic field outside is going to be 0 because the magnetization is 0 for S greater than A. But for S less than A, you have mu naught N. Yes?
We don't have an infinitely long.
We don't have what?
This is an infinitely long music because we actually are given a length. So would it still be?
Oh well, yeah, I
zero
think
and
still
that's
is going to be 0 because the magnetization of the object outside is 0.
Okay.
Yes.
I see what you're saying.
Yeah. We are talking about B. B depends on M. We don't have any free current here, so M outside this is going to be 0. Okay, the second part is so basically if you want to find this value of this, the flux at this point, this time, when it's just fully inserted into the wire, that's gonna be, pi is gonna be the integral of B dot dA. So we assume, a constant magnetization over this area. So this has a radius of B, and this one has a radius of A. So the flux over this loop is going to be what? Assuming that a constant magnetization. So that's going to be mu naught times the magnetization M, and the area that you need to consider should be what? Pi A squared or pi B squared?
Pi B squared.
Well, we say, the magnetic field outside the magnetized object is 0 for S greater than A. It is 0 for S less than A is given by that. So the flux that you need to calculate is going to be just only the portion of this that has a radius. Does that make sense? Okay, so if I just look at what I'm saying is you have a magnetic field only in this region of radius n. So it's like the magnetic field that you have is coming out from this end, right? So and only on this range. Outside this range it's 0.
Okay.
So